First thing, routing basics. And we're going to look at a number of items here, obviously, and in the basics of routings, routers and routing. And the thing that we have with networking, again, is the vernacular. What do words mean? So the router's job, and the router's job is to select the best path from one network to another network. It does that using metrics, and we'll look at different metrics as we go through this thing. But a couple of kind of basic terminologies here. The path is the route, and the process is the routing. The process that takes place when the packet comes into the router. What happens to it? What are the things that are going to happen to the system? Decisions are based on the destination packet's layer 3 address and the information stored in the routing tables. The layer 3 address, and that's what we've talked about all along, that routers are layer 3 devices. They're the devices that are going to find networks. And then we're going to use the MAC address to find the individual device that we're trying to get there. The routing table entries can be locally connected, learned dynamically from other routers, or created statically. What that means is, we can have a lot of different ways to do these things. And the default route is used if no other entry is available for the device. When we do the route table, and we're not to it yet, when we do the route table, I want to actually look at one instead of kind of made up one for the presentation. But they can be, and what happens in a router, the locally connected, everything that is locally connected, all the interfaces that are locally connected to the device, it knows about. You can look around in your house and you know who is in the house. You know what's in the house. Router does the same thing. It looks around and says, I've got this interface with this address, this subnet mask, or this prefix for IPv6. So I know it's on this network, and I've got this other interface that's got this one. And what they then do for the dynamic learning is use the routing protocols, and we're going to focus on OSPF. We're going to look at RIP, OSPF, and EIGRP. EIGRP is Cisco proprietary. But then it shares that information with all the other devices that are connected to it. I know how to get to whatever network. It tells these other routers, and if you think the things that we've been saying, all the addresses have to be unique. They have to be unique. Otherwise, the networks have to be unique. Otherwise, we're trying to send to two different locations to get to the same resource, which obviously is not going to happen. Statically, we go in and use the IP route command. Statically configured, the real issue with statically configured is once you statically configure it to a destination, then you got to statically configure it to get back. I had one of the former students sent me a project that he was doing. Why can't I get my answers back from my internet? I'm not gonna do his topology, but it was something, well, maybe like this. We will have some. He had something like this, and then we had these devices connected together, and he had routes to get there. He got there. He had routes to get there, but what he didn't have was a route to get back. You have to configure it both ways if you do static routes. Statics are kind of particularly if it is a very big network. Small network, not such a big deal, because honestly the topologies don't really change that often. Once you get them set up, you're probably in pretty good shape. But if you're in a network that the topologies change very much on, or it's a relatively complex network that we have to configure a lot of options, a lot of what goes on with those 3 routers, not such a big deal. If we had 20 routers, it becomes a lot bigger deal. A default route is one that is used if nothing else is available. It also can be used, here I go back drawing these circles again. It is also something that can be used if you're an end unit, an end device. When we look at these things, if we connect these guys together, the 2 end devices here and here, there's only one way out. So we could use a default route, send everything out. Then this guy's got to know how to get to the individual networks that are attached to these guys. Put some here, and these guys have network IP addresses on these interfaces. The router is going to know what those addresses are. It'll automatically say, hey, I've got these guys. We then configure the router to share those addresses with all of its friends. The router will then send the information about these addresses to this router. This router will then share it with the next router, so that the devices at this end, at the far end, can now get to devices at the other end, or any place in between. And this guy going to do the same thing. It will share information with going in this direction, and this one will share information going in this direction. And when they share that information using the routing protocols, each routing protocol has its advantages and its disadvantages. Once that information is shared, then we have a fully converged network, and we can get anywhere on it. But keep in mind, if I have statics here, and we started out with, if we have this, we can use a default on this guy because there's only one way out. We can use a default on this guy because there's only one way out. Where do I go to find things? And this one in the middle here is going to have some other things going on with it. We got there with the default route. Default route is used when nothing else is available, but there are times we can leverage it. You and I have default routes. I'll bet you that you and I have default routes. I know I do. I have a default because I only got one way to get to the ISP. There's only one way out, going to the ISP. So why try to do a whole lot of routing protocols to find all the other routes to do all of the information sharing if all I got to do is send everything out that interface? And if we have static routes created statically by us, we got to get there, and once we get there, we have to get back to. We have to have a route back for these things. The forwarding decisions, and this is one of the. Let me go back because I got some other things here that I went past. If the destination matches a single routing table entry, the packet's forwarded to that interface. If it matches multiple entries, it's forwarded to the interface for the route with the longest match and the lowest administrative distance. Okay, we've introduced a couple of terms here. The longest match means the route that has the most ones in the subnet mask, the one with the longest prefix. What I like to call the more specific route. So it's going to take the more specific, and down here we have this /24/19. It's going to take the /24 because it is a more precise definition of where we're going. The /19, more, I guess, networks could be involved in it. So the one with the longest, the lowest administrative distance. Administrative distance is another term. We'll get into it, but quick and dirty, administrative distance is basically how trustworthy is the route. And they go from 0, which the directly connected ones are. If it's directly connected, there's no doubt about it. It is there. To 1 for the statics, and I've always thought that was probably a mistake, especially with typos that we could make. But the static routes are going to be the second most trusted. The directly connected networks are going to be the most trusted. After that, we're going to get into the routing protocols. In the order they're going to go in are EIGRP, OSPF, and RIP. And we'll talk about those and the numbers that are involved with them, and I'll put a route table up here in a few minutes and show you where they show up in the. So in this one, and it's going to take it'll take the longest match. Going to take the 24 gateway. If it doesn't match anything in the routing table, the packet's forward to the interface for the default route. Default route is one that's going to be manually configured by us. And this is the one that uses all zeros. It uses an IP address of 0.0.0.0 and a subnet mask of 0.0.0.0. The zeros represent an any network situation. And any IP address, any network situation for this thing, so that it will then send everything that can't find a home in the route table to the default gateway, to the default route. If there isn't one, the big X there, it's going to drop the packet. Doesn't know where to do it. And this is where we get an error message back that says that the destination network is unreachable. Destination network unreachable error typically means we don't have a route. I don't know how to get there. Help me out here to do that. And that would be go check what's going on our router. When a router receives a packet, handles the packet in the following manner before the routing. Routing is the act of moving the information across the network from the source address to the destination address. What the routers do is forwarding or switching. We're going to have a couple of databases that are involved. We'll talk about the route table, and that's the thing that we're going to look at. Underneath the route table is going to be this thing called the FIB, the forwarding information base. And the forwarding information base is going to have the information of which interfaces to switch the packets, the interfaces to switch together to send the packet out the correct interface, to send it on its way correctly. Process switching, fast switching, and Cisco Express forwarding. Depending on which iOS version, basically the process is the same, the name is a little bit different, but switching takes place. We have this thing called the forwarding information base, and if you do a show, and you can see them typically, it's going to look a lot like the forwarding is done by using the adjacency tables that reside on the route processor on the interface cards that support switching. So the adjacency tables, who is connected to us, the adjacent routers, and we're going to have adjacencies. We'll form adjacencies, partnerships one with the other, that yes, I see you and I see you speak the same language as I do. You speak OSPF, you speak EIGRP, you speak RIP. So that we can now share information. You're adjacent to me. Tell me about all the things that you know how to get to, all the networks you know how to get to. And I'll share my secrets with you. I'll tell you how to get to all of the networks that I know how to get to. So the adjacency tables, what we're going to send the packets to, one from another. And then we have to have encapsulation, attaching the controlling information. The routing protocols that we will typically see, HDLC, High Level Data Link Control, HDLC is the Cisco proprietary. And every vendor has an HDLC, and all of the HDLCs are proprietary. So if we're going to connect our Cisco device to some other device, then we have to go to a standard. And the standard that we're typically use, particularly in labs, is PPP, the point-to-point protocol. Point-to-point protocol has been around for a long time. Point-to-point protocol was the layer 2 encapsulation protocol when I was using dial-up routing. And that was, 20, 30 years ago. Probably was 30 years ago. Pretty close to it anyway, when we do there. The routing process, and remember, process is the action that takes place here. We're going to talk about metrics and all that other good stuff. And let me start a packet tracer here and look at some route tables. And I've got one, and I usually pick the wrong one consistently. That's got both or two different routing protocols, so it's easier to see. And I think I remember the name of it. This one kind of sort of says it is. When I talked this morning about loopback addresses, this looks like, hey, you've got nothing there. What I've got here is, if I go into this thing and do a show IP interface brief, I have a bunch of interfaces. These are LO loopback interfaces. That allows me to build a big routing topology and play with routes, different routes, without having to do any more configuration than that. If I show, and this is all IPv4, IP route, and that'll be the default, we get some of that information. This has got a whole bunch of stuff going on with it. We've got Ds here, and then Ds are EIGRP. Actually, these are all, well, we've got a RIP in here finally. We've got a RIP route. And when we go across this thing, 192.168.14.0, this is the destination network and the subnet mask. We have R's here, we have C's here. These are the directly connected. These are the networks that we're going to tell all of our friends about. We also have this L here, and you notice it's a /32. This is the actual IP address of the interface that this route is attached to, directly connected. We have here a couple of different things we're talking about here, metrics for this. The metrics, the administrative distance, the order that this goes in. Over here on the left is going to be the protocol that we're using, and we've got a table at the top that'll tell us what the protocol is. D, if you go up here, is EIGRP, the Cisco proprietary one. The destination network, and it will show with the CIDR notation, but when you configure them, you gotta use the subnet mask. The administrative distance, and it's different for every protocol. And you notice here that we got a 90, and down here there's RIP, R for RIP. If you look up there, it's 120. And then we have the metrics, and the metrics are different for each of the protocols. And this one is 131072. Big number. When we do EIGRP, we'll look at it, and you'll see why it's such a big number. These get even bigger down here for some of them. And down here they get smaller depending on where we're going to, how far we're going with these things. And you notice that RIP here is a real small one. RIP uses hop count. The EIGRP uses bandwidth and delay. And then the VIA is what is the next hop address. What's the IP address? The adjacency. What's the adjacency address that's going to be used for this thing? And then the interface that it goes out. This is just how long it's known the route. When we talk about in terms, and we'll look at these things multiple times, that maybe it'll make a little sense after we get through seeing it time after time after time after time. The addresses, but the protocols use metrics, and the metrics determine what the best paths are to get from one to the other. Best path to travel through the network: hop count, bandwidth, delay, cost. OSPF uses cost. RIP uses hop count. EIGRP uses bandwidth and delay. Get from one to the other. And the bandwidth that it uses is the lowest, or the lowest. Yeah, the lowest bandwidth is going to be what it uses to calculate. Goes from one to the other. So you may have this really high speed and one really low, slow link that it might not use what you think is the best path. It uses based on its algorithm, the determination it makes. Algorithms initialize and maintain the routing tables, and the routers compare metrics to determine the optimal routes. And these metrics differ depending on the design of the routing algorithm used. Yes. What is going to happen here, which one's going to be put into the route table, is going to be based, and we'll bring us back over here. If I have multiples, and let's go to this guy, I think that he has, both of these other two both have, show IP route, both have RIP and EIGRP running on them. Yeah, we have a couple of RIP routes here, and this guy's then going to re-advertise them into EIGRP because the rest of the network is running only the EIGRP network, EIGRP protocol. But the determine which one. The first thing we're going to do, where was I going? The first thing we're going to look at is the administrative distance. And if we have two routes to a location, two paths, two ways to get to a location, and we have two different routing protocols, it's only going to display in the route table the one with the lowest administrative distance, the one that is the most trusted. And that's what administrative distance is. How trustworthy is the protocol that we're using. Indicate the next hop as the optimal path to the final destination. In this one, I don't know, I'll keep flipping back and forth. And this one, this router down here, we don't have a whole lot of choice. It's only got one way out. We could use a default route here, but I didn't do that. For these guys, we've got a couple of different paths to get from one location to the other. And then it may even show that on one of these, but I don't see it there. one of these guys should have, and it does down here, has 2 routes, and they're equal cost routes, 3072. And the reason I was saying that is looking at this guy to get to this network here, the one in the middle, this network here, we've got 2 equal cost paths to get there. So we should have 2 routes, and we in fact do have 2 routes in this thing in order to down here at the bottom, and it was the one at the bottom. 90 tells me it's EIGRP 3072, 3072. So we have 2 different ways to get to the 130 network, from one to the other. Yeah, I'm looking at 100.2 and 120.2. So we have two different outlets, 2 different outgoing interfaces, gig 01 and gig 02, in order to get there. So these things will, in the routing, will share the load. If checks the destination address for the receive packet and attempt to associate the address with the next hop based on the route table, based on the forwarding information base. Communicate with one another to maintain their routing tables through the transmission of a variety of messages. The routing protocols are the things that we're going to use to do those transmissions. The router, when it starts up, only knows about things that are connected to it. That's it. And it then will advertise, bring this over one more time, will then advertise using a router command, using a network statement that says using the EIGRP protocol, and this is the autonomous system number, and we'll look at those when we do the configuration. Autonomous system number, which says, hey, talk to all of the routers that are running EIGRP that are in Autonomous System 30 and tell them that I know how to get to these guys. They're connected to me. I'm going to advertise these networks. You then tell that to your adjacencies, to the adjacent neighbors, who tell it to tell a friend who tells a friend who tells a friend. And then eventually we have the network populated with the networks or with the paths using the calculations of those algorithms, whichever one we're using. This is, and I think we get this one again, preventing routing loops. The routing loops issue really is kind of I'm going to say kind of a rip thing, although it could happen with the others, but routing loops could happen because things don't get updated immediately sometimes, especially in RIP. RIP is a broadcast protocol. RIP v1 is a broadcast protocol. Broadcasts its entire route table every 30 seconds. So it could take a while to get some information from one to the other. In this case, this network over here goes down. It then gets advertised as down when we do this thing, and then the split horizon is the thing that allows that to happen. And I don't know why my slide doesn't do, here, the routing process, the routing metrics. This one actually has some information in it. So the techniques that we use here are split horizon, that prohibits the router from advertising a route back to the interface from which you learn. What does that mean is, if you tell me something, I can't tell it back to you. Where would that happen? In the one that we're going to see, the network goes down, and you've told me how to get there, and you don't get the update that the router's down, and you try to get there. So I say, oh, I know how to get there. You go in this direction, so we will go into a loop. A route poison is advertising something as a failed route, and this is, again, a RIP situation. RIP allows us 15 hops. 16 is infinity. 16 hops, 16 routers is infinity. And we can have 15 routers, 15 hops. After that, the route gets marked as unreachable. Advertising a failed route using a special metric called infinity. The other routers will consider the routes advertised with an infinite metric to have failed. Poison reverse, enhancement of split horizon that sets the metric to infinity and advertises the route as unreachable. What poison reverse actually does is we use the route poison, but it allows us to violate the split horizon rule. And a passive interface just simply says don't play in the game. If you have an interface that you don't want to send basically updates, does not participate in OSPF, then you can do a passive interface for any of the protocols. Just basically says don't play. You can say, yeah, why don't you just not advertise it? We could do that. There are situations that we want them to get information but not send information. For instance, we probably wouldn't want to send information to our... So let's try this thing again. This route goes down, so then we're going to block it over here. But this guy is now told this one that, hey, the network's down. But B says, hey, I know how to get there. So C then sends that data to B before it gets updated. He's now put a new route to get to the 51 network into his route table. And based on all of the provisions, he's not going to take any more information. So then we get the packet here that's going to 51.3 gets to C. C sends it back to B on around until we just start sending it back and forth. These mechanisms up here, and the reason that one happened is back, let's see if we can get back here. Back here, after this one went down, that B told C that it knows how to get to 51.32. So C now sends its data to B, and the updates from one to the other. The packet comes in, sends it to C, back to B, on around. So we create a loop here. And these techniques, loop preventing techniques, are designed to prevent that, particularly the split horizon. The split horizon, you tell me the D, we'll call it the green network, how to get to the green network. C tells B, and B tells A. So it's going to go to B, to C, to D. This goes down, and before D can update C, if we don't have split horizon, it says, hey, I know how to get there. So C will now send that traffic here, and we'll just go back and forth, bouncing around, because B is still going to go in the right direction. Split horizon, you can't tell me something that I told you. You can't tell me about a route that I told you. Route poison, infinity, not available. That's what this one should be marked as here. The poison reverse, regardless, I'm going to set the infinity and advertise as it infinity. And a passive interface, I just don't want to play. I don't want you to play in the routing game. The default route, also called the gateway of last resort, and we can do one of those here, since we can't actually do a default route on this guy. Gig 00, what I need is the IP address of the next one. So gig 00.192.168.50.2. In order to configure it, and remember it's going to use this since we all have these other routes if nothing else works. So it's just a simple IP route 0.0.0.0 with a subnet mask of 0.0.0.0, and it was what, 192.168.50.2, I think. So now when I do a show IP route, this shows the gateway of last resort is to network 0.0.0. That's the any network. It also shows up down here as an S as a static. A static with a star means that it is in fact the default route when we do those things. And via is going to be the next hop address. So default route, if I don't have anything else, nothing in the route table matches, send it there. And then my thing is send it there and let the other guy worry about it. So the default route, the address is 0.0.0.0/0. That means that no bits, the subnet mask, the 0.0.0.0. Direct frames that don't have an explicit next hop. There is no entry in the routing table for the packet that came in. There is obviously one in the routing table for the default route. Gateway of last resort shows in the show IP route command, and that's how you know that we have a default route set. And again, I said there are a couple of a couple of labs off and on as we go through. I want to save them and consolidate them for the ending here, because it doesn't make any sense to me to do them like the next topic that we have in here is this thing called first hop. We're going to have two of them. We're going to have Cisco proprietary, HSRP, and the standard VRRP. HSRP is hot standby redundancy, or hot standby router protocol. VRRP is virtual router redundancy protocol. Provide a transparent failover first hop device or a default router for these things. Proprietary Cisco protocol, HSRP, assigns virtual IP addresses to a group of routers. The virtual router redundancy protocol basically does the same thing. There are a couple of differences, and I want to demonstrate HSRP, and then we'll talk a little bit about VRRP. If you want to play with this, you can, but you'll probably have to do it in Packet Tracer, because I think that the Boson labs aren't available to you. I think they moved these into the CCNP. So the VRRP, transparent failover at the first hop. What does all this mean when we do that? Actually, we got an image coming up. What all this means is that we have multiple routers configured here that are ready to forward our information, the multiple routers here that are ready to forward our information to the cloud or to the ISP. One of them is going to be the active router, and the other one's a standby router. Standby router is waiting for this guy to have a problem, to fail. Once that happens, it's going to take over. In the middle here, we have a virtual router, which has an IP address and a MAC address. And I think the MAC address is really a big deal based on what we've talked about. How we get from one device to the other device, we're going to use the MAC address. The default gateway for these guys is going to be the virtual router's IP address. It's going to control where the data packets go, which physical router the data packets go. So one goes down, the routes continue, or the data flow continues. We keep going. What you might want to consider here, and this is another one, and there are a couple of places that in Roanoke that I went to, talk to people about that did that. We have an ISP. The active router goes to our high-speed ISP, and then the standby router may go to the cable modem or something like that. So that if this one fails, this one takes over, it goes someplace else, because what happens if the ISP fails? And we'll look at how to detect that here in just a couple minutes. The networking protocol designed to protect the default gateway. First hop is our default gateway. The first hop is first hop for our enterprise, allowing two or more routers to provide backup for the addresses of the first hop router. Transparent redundancy, transparent failover. We should never see the failover happen. It's going to happen automatically. When this one says two or more routers, in the case of HSRP, we can have exactly one active router and one standby router. We can have others configured to use the protocol. They're going to be in a listening mode. When we get to VRRP, we can have multiples configured to be the backups for it. So HSRP includes the HSRP protocol, the default gateway, redundancy using one active, one standby router, Cisco proprietary. VRRP is an open standard alternative to HSRP. And gateway load balancing protocol, which is not part of CCNA, but it's something to know about, is a Cisco proprietary that balances the load. If we have two of these running, they don't really do any load balancing unless we do a manual configuration. We'll talk about that when we look at configuring these things. One of them is just waiting for the other one. So this is what it looks like. HSRP, we have and this has got the two here, the standby gateway, the active gateway. HSRP is communicating among these things, and we're going to have another election. We're going to elect the active, and the active is going to be elected. And if the priorities are all the same, it's going to be the highest. In switches, we tended to go with the lowest of. In routers, we tend to go with the highest of. I think this is probably as good a time as any. Let's look at, see if I can get through this thing. This is almost completely configured. I've got the outside interface configured. And we talk about this like, okay, yeah, you can just go here, you can go here, but these guys up here got to know how to get back to you. They got to have a default gateway. We're going to have, different physical interfaces unless we configure an HSRP, which I've done, so it can get back from one to the other. But this router over here is configured, group 1, priority 105, preempt some commands, and we're going to look at some of that stuff. This one over here is going to be eventually the standby router. I want to do a couple of things with it to demonstrate some of the kind of the quirkiness, I guess, would be a reasonable word of this protocol. The way that you configure it is with the standby command. Don't know why that is, but it is the standby command. I can show an IP interface brief for this, and I have 00, and in this case 00 is the outside interface and 01 is the inside interface. They're both up. They both have physical IP addresses. To be sure, that's the way it is. Yeah, the 00 is the outside and the gig 01 is the inside. So in order to configure this, it's another pretty straightforward configuration. It's just a matter of keeping all the facts. So let's go to interface gig 0. Actually, we'll go to config first, I guess, huh? Interface gig 0/1. And we're going to do standby version 2 because version 2 is on the other interface. Now we have to have a standby group, and this side is standby group 1. So we'll do standby 1, and if you don't do the 1, and that's what I usually do a lot, it assigns it to standby group 0, and you put in the IP address 192.168.1.1, which is the IP address of the virtual router. It says, hey, you've got a mess here. Now I think I got to probably say IP. So we had that, and it's going to be IP 192.168.1.1. So group 1 state is initiating, and we'll wait here for a few seconds see if we get it going, get some. So the init mode, we'll look at the modes in a minute. The initialization mode. Show standby. There we go. We're going from speak to standby. We're going through the process, speak and talk to the other guy. This is now the standby interface. If I wanted it to be the active interface, I could assign it a higher priority. So let's do standby 1, STNDBY 1, priority, and let's make it, the other one was 105, let's make it, and we'll wait here. Based on what I said, it should become the active interface or the active router. The reason it doesn't is because we have this preemption control, and we have to configure the devices to, if they are the higher priority, to preempt. If we don't configure it, preemption is not going to take place. Standby 1, and see if it will STNDBY 1. So I almost made that mistake. Standby. Fortunately, it saved me. Preempt. Now we immediately go from standby to active. Are we really the active interface? And then the physical interface here is 1.3. And let's just do a trace route to 2.5. So we can go in here and do a T 192.168.2.A. So it went to 1.3. And with any luck, it's going to get there here in a few seconds and get back. So we got to the 2.5 by going through the 1.3 interface. I really don't want this one to be the active one, so I'm going to go in here, and we still have this, and let's make it a priority group. Let's do standby 1, priority, and we'll make it 100. When that happens, the other guy, I think, is configured for preempt. We'll see if they'll talk here just in a second. Hello, sent, there we go. So I've now, it took a few seconds there as you saw when I did that. We're now the standby. So did the active router change? Because I'm still going to the same default gateway. Let's go to trace route to the 2.5. And so we went to 1.2 this time, which is the physical interface, the physical IP address of the other router. So if this interface fails, and we can go in here and make this interface fail, as inside it was gig 01, right? We'll make that interface fail. Then this guy should, here in just a second, become the active router. When I fix this one, I want it to reassume the duties, and that's what the preempt is all about, to do that. So we can turn it on, we can go and do this and see if we actually can still get there. So the 2.5, trace route 2.5 goes to 1.3, to the right-hand one, and comes back. So that one does pretty well, but what if this interface, the one going to the ISP, fails? The ISP fails, something happens there. So let's turn that one off. Didn't matter. I made it crazy. We're gonna have to restart it because figure out that it's not responding. Cisco wants me to describe the problem. Problem is I broke it. So let's get a chance to do the configuration again, and then I do want to show conceptually one other thing for P, and this one here. So let's go in and just leave it where we were. The default priority, by the way, is 100. If we don't change anything, the priority is going to be 100. So this is interface gig 0/1, I think, right? And so we're going to do standby, standby version 2, and then standby 1 IP 192.168.1.1. And I'm going to go ahead and do a preempt because we're going to need that in a little bit. Standby. Since it is 100 and 100 is the default priority and the other one is 105, nothing's going to happen. So now let's go in and see if we can make the gig 00 fail without crashing the system. Gig 00, and turn it off. And this is the active router on the inside interface over here. Now then, let's try to trace route 192.165. And we go to the 1.2, which is supposed to go, and it's going to stop there because it can't go any farther. 1.2. And this is one when I talked about earlier, wherever trace route stops, start your troubleshooting there. So we got a problem. What happens if the other side fails? We're in great shape as long as we're inside our own network. But what happens when the outside interface, turn this one back on, we can configure an interface tracking to do this thing. So let's go configure IF, and I think that, let me be sure that I'm on the right one. Interface gig as the other one. I'll be sure I'm on the right router too. Let's see. So we're interface gig 01, which is our internal. We can do standby 1, and then config mode. Well, I don't know what. Okay, I spelled standby wrong, huh? Again, standby 1, interface gig 0/1. Oh, I went to config T again. Okay, standby 1, and now we get these. We got preempt, timers, track. What we can do is track, and then we can track gigabit Ethernet 0/0, the outside interface. If it goes down, it will decrease the priority of this interface. I'm going to do a show standby, and this was in the, this is where we got 01 here, where's 00? Standby 16 virtual IP address. Oh yeah, the virtual MAC address is also something I want to be sure to talk about. The last 2 bits, and this is version 2, the last 3 bits represents the group number. This up here, 00 is group 2 down here, group 1 on the internal interface. This is the one I was looking for. Priority is 105, configured 105. So we have track the interface gig 00 up decrement 10, which is the default decrement. So it's going to decrease the priority of this interface by 10 if that interface that we're tracking goes down. So let's make that interface that we're tracking go down, gig 00. Let's make it go down. And then let's go back here and look at see if it changed the priority. It's working right. Tracking, so it went to standby. This one now says that it's configured to 105, the priority is 95. It had actually decremented. We had the preempt enabled on the other side. And now when I try to do my trace route to 192.168.2.5, we go to 1.3 and we get there. Some configurations that take place in the hot standby routing protocol, the HSRP. We have standby routers, 2 configured to allow us, then this one is redundancy. When we talk about redundancy, I guess it really doesn't like me today, huh? I'm not going to save this thing. What I want to do is to talk about before it crashes, which is going to do here in just a second. I have to bring it back up. Is how can we take advantage of the 2 routers? And the way we can take advantage of the 2 routers as this thing starts is by configuring multiple groups, and this one is configured that way, configuring multiple groups on the interfaces. What we have here is we have group 1, which is the active interface on this guy, and group 10, which is the standby, and group 10 is the active over here, group 1 is the standby. We still have our redundancy configured, but now we have about half of our IP addresses that would go to group 1 as the group 1. Group 1, I'll get it. Group 1 is the default gateway, and about half of our IP addresses that would go to group 10 as the default gateway. That way we don't have one that's just hanging around waiting for a failure to take place. You make the manual load balancing by creating multiple groups to share the load so that you don't have one that really is just waiting for a failure, doing nothing, just hanging around, smoking and joking and crashing. The first hop redundancy protocol, again, HSRP, the Cisco proprietary. Same sort of thing that we saw a little earlier. We have the gateway, the 70.1, 172.30, 70.1, 172.30, and there should be a 70 in here. .1 to go there. It's going to manage which of the interfaces or which of the routers get used, and in this case it shows it's going to WAN 1, WAN 2, which kind of makes to me a little bit more sense, because if this one goes down, if this interface goes down, the route to it, or if the ISP goes down, then it'll automatically shift over from one to the other. We have an active gateway and a standby gateway, active router and a standby router in this protocol to do these things. HSRP designed to provide transparent failover, and hopefully the demo showed that it is a failover, it is transparent, which means that we don't have to do anything. We have to wait a little bit, although in real equipment, if you are pinging, doing a constant ping with the -T switch, you lose probably 3 or 4 pings. The shift over actually happens. Cisco proprietary and the RFC 2281. High network availability, transparent failover for a default gateway address. We configure them with the standby protocol. Standby, one word to take away for HSRP is standby. Standby to configure it, show standby to see it in order to use that particular protocol. One router is active and the other router is the standby device. And again, we can have multiples configured for HSRP, for the standby protocol, but only one of them is going to be active and one of them is going to be standby. The others are going to be in listen mode, waiting for a failure to happen so they can assume one of the roles. Election process, the highest priority wins. If there is a tie in the priority, the highest IP wins. Virtual gateway, the virtual device, the one that manages the flow, and we have to have the communication between the two routers in order for that to happen. Virtual gateway provides a virtual MAC address, and again, to me, the virtual MAC address is a pretty big deal, because if we just shift it over, we're going to have to wait until the ARP caches out, or we get some sort of an ARP update in order to make the changes in the ARP table, because we're going to go to the MAC address for that IP address, whichever one we are sending the information to. I want to do that. Designated devices fail. Standby device will assume control of the MAC and the IP address of the HSRP group, and a new standby device may be selected at the same time if there are other devices configured. That's where the may be selected, but we have to have more than one configured. Only one is active and one is standby in this one. Priority number, active router higher priority than the standby router. Priority number 100 is the default. Preemption, and what I tried to show when we were doing the configuration is that these don't preempt by default. I assigned it a higher priority and nothing happened until I did a manual preemption on it. So when an active router fails, preemption selects the standby router to become the active. Depends on the priority field in the HSRP packet. In the failure, it will activate the other one. What would happen if we don't have preempt enable when the active router comes back online? Unless preemption is enabled, it won't take over. And that's why we have to configure the preempt command, which we did on that. High priority wins. Equal priority defers to the actual higher. Couple of messages. When one takes over, the higher priority router preempts the lower priority router, it's going to send a coup message. So it's going to send this coup message, and when it gets the coup message, the other guy is going to resign. When it resigns, the lower priority receives the coup message, which is a hello message, from the higher priority router. It'll change to the speak state and send a resign message. And then we have the hello, which is the heartbeat. The hello is, are you still there? The heartbeat message, and that's the way they know that they're still running, that I should still be the active. Okay, I'm not getting this heartbeat message. Then I should take over. State here, and this is a little bitty one here, the HSRP states, one that you can actually read. The initial, the init, is the start state. We saw that one, and then it kind of jumped. We didn't see the learn, the listen. We kind of jumped to speak, but that kind of sounds like spanning tree, doesn't it? Cisco, the terminology a little bit becomes consistent. So we have the initial, the HSRP does not run, the state entered through a configuration change, an interface. When an interface becomes available, the learn, the router has not determined the virtual IP address, not yet seen an authenticated hello message from the active router. The router wants to hear from the active router still. It's still learning about things. So listen, the router knows the virtual IP address, but is neither the active router nor the standby router. It's listening to the hello messages from those routers. The speak state sends periodic hello messages and actively participates in the election. So speak, we're going to maybe think about it doing the debate and doing the election. Cannot enter the speak state unless the router has a virtual IP address. And then the standby state, candidate to become the next active, and then the active is the one that's going to be doing the packet. The versions, group 1, group number 0 to 255, the default version for HSRP, and it uses a multicast address 224.0.0.2. The virtual MAC address is the last 2 bits. This is a hex number, so that's why we have 2 bits go to 0 to 255. This is one I've seen on test banks at least. The AC, and it'll ask you what does the last 2 bits, what do the last 2 digits mean? And it's going to be 000, 0C, 07, and C's show up an awful lot in Cisco MAC addresses. AC, XX, the XX is the group number, the HSRP group number. Version 2, a lot more groups, not compatible with version 1. Different multicast addresses, still got the 2 in it, but it's a 102, 224.0.0.102. Multicast, typically in the big list we looked at yesterday, most of them started with 224.0.0. something. The virtual MAC address here, since we have 4095, 0 to 4095, 4096 possibilities, we have 3 bits available for it, and it ends in the last section there. The last was 16 bits. It's going to start with an F for IPv4 and a 0 for IPv6, but the last 3 bits are still going to represent the group number for these things. Version 2 has support for IPv6. Authentication is removed. Didn't really work all that well. Insufficient security for these things. And again, a couple of labs that we will save for a little later on. VRRP, Virtual Router Redundancy Protocol, is the standard. Works basically the same way. We're doing the same thing. We're going to have the ISPs, the WAN. We're going to have in this case, we're going to change the names of them to master and backup instead of the active that we had earlier, the terms that we had earlier, which were the active and the standby. I always want to stay back up here, but these are the master router and the backup router. We can have multiple backup routers in VRRP, and we can have multiple routers configured as the backup router. Basically the same, not basically, it's the same concept. It's just a standard instead of the Cisco proprietary. This is another one of those that Cisco has a better idea, and then when the better idea, everybody else says, hey, that's a good idea. Let's go create a standard for this. And once they create the standard for this, sometimes Cisco takes the proprietary out, sometimes they don't. In this case, they've left proprietary in. It has a couple of quirks, as you saw, one of which, the biggest quirk, I think, is the preempt. VRRP preempts by default. HSRP does not. So in this thing, we're going to have the VRRP, the IP address, same thing, 10.10.0.1, virtual router group IP address. The virtual router backup 10.10.0.2. This one actually manages the physical IP addresses. Eliminates a single point of failure, just like HSRP did. Group of routers share a single virtual IP address. Uses the industry standard protocol, RFC 3768. Has a master router, handles all of the virtual address that goes to it. The remaining routers are going to be in the standby group. Take over if the master router fails. And again, we can have more than a single standby router in the VRRP group. Benefits, and these are, hopefully kind of makes sense. Redundancy, configuration of multiple routers is the default gateway. Load sharing allows the configuration across multiple routers, same way that we did with HSRP. It does not automatically. Ensures that you equally distribute the traffic among the routers, support for up to 255 virtual routers on a single physical interface. For multiple IP addresses, manage multiple IP addresses including secondary addresses. It allows VRRP to be configured on differing subnets but serviced by the same VRRP group. We have multiple addresses, secondary addresses, multiple addresses on a single interface. Preemption, manual substitution of the virtual router. Preemption is enabled by default on VRRP. Uses an MD5 authentication. Multicast address, it uses 224.0.0.18. VRRP object tracking. It does tracking, but it does it in a little bit different manner than HSRP. We track the interface. In VRRP, we set up an object to track, and then we assign the object to the interface in order. The effect is the same, that if that interface goes down, the priority will change, and then we can automatically fail over to the one that will lead us to go there. It's just that the process and the terminology is a little different. The HSRP VRRP comparison, Virtual Mac HSRP AC something something, HSRP version 2 for IPv4F something something something, and then 0 something 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 for IPv6. VRRP 01 something something, where the XX down here indicates the group number in hex. The multicast address is 224.0.0.2, 102, and then 18. The number of active routers is 1 for each of them. The number of standby routers, 1 for the HSRPs and many for the VRRP. Preemption is disabled by default on HSRP and enabled by default on VRRP. Again, two protocols configured a little bit differently, but they are designed to do the same thing. One's a Cisco proprietary, other is a. This is a reasonably good summary of the protocols, including GLBP, which is the Gateway Load Balancing Protocol. HSRP, UDP encapsulation using port 1985, IP encapsulation 112, and I think 112 using 112. 112 is the protocol number on that one. UDP for GLBP using port 3222. Cisco proprietary for HSRP, GLBP, VRRP is going to be the standard. Priority for each of these, for all of them, the default priority is 100. The MAC address for the two protocols that we have looked at, the groups, the last digits are the group numbers. The GLBP up to 4 virtual MAC addresses per group for it. The timers, the hello timer for HSRP is 3 seconds. The whole time is 10 seconds, which is about what it took us, I think, when we did the manual, when we did the changes on it. Those are configurable numbers. VRRP, 1 is the default. It does its time calculation, as you can see, a little bit differently. GLBP, the same hello and hold time. The hello messages active and standby sends the hello messages. In VRRP only the master sends them. And then the hello messages in GLBP are messages in all the router groups. GLBP uses, go down a couple of the active virtual gateway and actual virtual forwarders. The actual virtual gateway is the control mechanism. The forwarders are the ones that do the work. And you can have up to 4 forwarders in a group. So the preempt, go back to the preempt. If a router is a higher priority than the active router and preemption is configured, it'll take over using the coup message. By default, VRRP routers are configured to preempt, and GLBP allows a router to preempt and become the active virtual gateway if it has a higher priority than the current active virtual gateway. Active Virtual Gateway is the manager. GLBP is a little bit different. It has multiple devices, and the protocol does the load distribution, the load sharing. Whereas in the HSRP and VRRP, we have to do a manual sharing in order for those to happen. The active router, the numerical higher priority for each of these, equal priority for both of these, the higher IP address wins. And over here, the equal priority, the higher IP address wins. Backup router, another selected if the HSRP and others remain in the listen HSRP state. This is we can have multiples configured, but only one of them is going to be the backup. In VRRP, we can have multiple backups. Tracking decreases the priority by 10. No tracking option. We have object tracking in VRRP, not interface tracking to manage it.